Hello, welcome to our next set of stats notes. We're doing section 4.4. This is our last section for probability. We'll see in the next chapter, we'll hit chapter 5, and then that's the last chapter we'll hit for this first unit, the first exam. We'll kind of see how we can kind of tie this probability we've been covering in chapter 4 back into statistics that we've been doing. This is our last section on probability. So after chapter 4, we're kind of moving on from probability and more back into statistics proper. So this section, we're going to deal with counting, which sounds silly when you think counting, you think grade school and learning how to count. But the difference here is we're going to be counting really large sets of things. Times where we'll have millions or billions or even more options or possibilities, outcomes. And so we need kind of techniques or methods for counting rather large sets of numbers that we will be using for our probabilities, for all the good options over the total options that we usually use for probability. So, a lot of times we have to look at the different number of ways something can happen, the number of possible outcomes, number of ways a task can be performed. So we're looking at all these different options of, number counting kind of thing. Sometimes you can list the possibilities, and we saw that in the previous sections. And we'll show an example down here at the bottom, but lots of times you can't. And so this section, we're kind of learning the techniques to calculate the number of possibilities, the number of options, when you can't just sit there and list them out and count them, in the times when it's impractical to do so. So the rule is mentioned here, but I want to go ahead and show this example first without the rule, and then we'll see how the rule works. So let's come back. We'll come back to the rule. So first, let's look at this example. When John gets an ice cream at his favorite spot, he always gets either a waffle cone or a bowl. So first off, he's going to choose between a waffle cone or a bowl. Those are his two choices. He always gets 2 scoops, so he's going to get 2 scoops of ice cream. And that ice cream could be either chocolate, vanilla, or mint. So those are the 3 kinds of ice cream he likes to get. How many different ways can John order his ice cream? So we're looking at the number of options for John getting his ice cream. So first off, when he first walks up to the counter, he chooses, waffle cone or bowl. So he has those 2 choices, a waffle cone and bowl, at the beginning, right? 2 options for what he's going to put it in. Is it going to be a waffle cone or a bowl? And then he gets his first scoop, and he's got 3 choices, right? 3 options for his first scoop, because the first scoop could be chocolate, vanilla, or mint, and all 3 of those would work. So he could have chocolate, vanilla, or mint. Either way, whether he gets a waffle cone or bowl, he can choose between chocolate, vanilla, and mint. And then after he chooses his first scoop, if he's not very picky, he could pick any one of those 3 options again, right? He's still going to have 3 options for the second scoop, because he could get chocolate ice cream twice, right? Chocolate and chocolate, or he could get chocolate and vanilla, or he could get chocolate and mint. Maybe he likes mint chocolate. So all those would be options. I'm going to start drawing lines here just to kind of show that what's connected. So you could get waffle cone chocolate, or you could get waffle cone chocolate vanilla. You could also get waffle cone vanilla and chocolate. That would be a way to do it, because now here we're talking about the order of the scoops. The bottom scoop is vanilla and the top one's chocolate. And you could do vanilla or vanilla mint, and then you can do the same thing with mint, right? You can get a chocolate scoop second, or you can get a vanilla scoop second, or a mint scoop second. So you can see all those different ways of getting this. And then he does the next one. Now he's got his second scoop, and that one can be, on his bowl, he could have, his chocolate scoop first, and then his chocolate, vanilla, or mint. So there's 3 options there. I should give myself more room. That's the hard part about doing this chart, and why we won't use this very much, because you can see how even with this small set of numbers, this gets pretty impractical. Chocolate, vanilla, or mint for the second one after the mint. But if you look at this, you can see we've listed all the possible combinations. Now we can look at all the different things you could get. You could get a bowl with chocolate and vanilla, or you could get a bowl with mint and chocolate, or you could get a waffle cone with mint and vanilla, or a waffle cone with chocolate and mint. And there's all these different options. And so we actually can find the number of options if we just count how many there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And there's 18 options. So he walks up and says, okay, I'm going to get either a waffle cone or a bowl. I'm either going to get chocolate, vanilla, or mint. And how does that? He has 18 possible options. But like I said already, you can kind of see that this is not the best way to do this, especially if you had maybe more. Most ice cream places have more than 3 choices. You walk into some of those places that has 30 flavors or something, you can see how that this would get pretty ridiculous pretty fast, especially if he has more than 2 choices for what he's going to put it in, or if he gets more than 2 scoops. So you get a lot of options pretty fast. So that's why we typically use the multiplication rule. This is one of the most powerful, important rules for finding probabilities when you want to work with bigger sets of numbers, and it's the multiplication rule. And it says when you're counting the number of possible outcomes, you're looking for the number of different options for sequent events, you can multiply the number of possible outcomes for each event. So we're going to multiply the number of outcomes for each event. So they're going to do this with generic terms. So they're going to say if n1 is like the number of the first choices, and n2 is the number second, and so on and so forth, you would multiply n1 times n2 times n3, so on and so forth until you hit the end. But for our example down here, a little more concrete, you can see that in the first place we had 2 options, waffle cone or bowl. The first scoop we had 3 options because we had chocolate, vanilla, and mint, and then the third one we had again 3 options, chocolate, vanilla, and mint. So we could multiply 2 times 3 is 6, times 3 is 18, and get that same number of 18 options we got without having to make this huge chart and graph. We could just multiply and get 18 that way. And so this is the multiplication principle at work. It's a really powerful rule, and I use this all the time if I'm trying to calculate a probability. I just think about how many options there are at each stage. You know, a lot of probabilities end up with more than one thing. Like I think about playing cards where you draw 5 cards from a deck. Well, every card you draw, you're going to have options of what you could get at that point. If you roll a die, well, if you play Yahtzee and you roll 5 die, now you got 5 different events. Each die is its own event. So that's why I use the multiplication principle a lot in real statistics situations. You know, to calculate statistics, it's a very powerful rule. The fact that we can multiply the number of each, the outcomes for each part, each event, and just multiply those together like that and get the answer. So let's use that on some questions. So example, Jan is picking 6 numbers for a Powerball. So now we play the lottery. I want to see if, the probability of winning, or so they're going to figure that out. So 6 numbers for a Powerball. If you can use 1 through 20 for the first 5 numbers, and 1 through 45 for the 6th numbers. So notice that's our options right there. 1 through 20 for the first 5 numbers, and 1 through 45 for the 6th number. How many different Powerball tickets are possible? So in order to calculate any probability with this Powerball, they're going to have to figure out the total number of options. And that's what they're going to do here. So we're going to figure this out. Now, when I do this, what I typically do is I think about what's going to happen, and I make a little line for each one. So I think, okay, the first 5 draws. So they're going to have 1, 2, 3, 4, 5 draws. So I'm going to multiply the number of options for all those, and then they're going to have a 6th draw that's going to be the other number. So I'm going to have to figure out the counts for each one of these. So I start off, we got 1 through 20 for the first 5 ones. So the very first one you get, well, 1 through 20, that's 20 options, right? You could get 1, 2, 3, 4, 5, all the way up to 20. That's 20 options. Now, of course, when you play Powerball, you can't get the same one twice because they have that machine with all the balls that rolls around in it, and they pull a ball out, and it's gone, it's out. You can't get it again. So every number has to be different. So once they pick one of these numbers, 1 through 20, the next number has 1 less option. Doesn't matter which one they picked here. Maybe they picked 7, maybe they picked 14, but one of those numbers is gone. And so now instead of 20 options, there's only 19 options. So there's 1 less because they took one of them out. And then they go to get the next one. And now this one, they've took out 2 balls. So instead of the original 20, now there's only 18. So now there's 2 less. And they go to get the next one. Well, now they've taken 3 balls out, so now there's 3 less. So now there's only 17 options. This next one, they're going to pull 4 balls out, so there's 4 less. So now there's only 16. Now we get to the last one. Remember that the last one, we get to choose through 1 through 45 because there's all 45 balls in there for just this one Powerball, the 6th number, special one. But because we took out 1, 2, 3, 4, 5 numbers already, right? We took out numbers between 1 and 20. This one actually is still limited. It's going to be 5 less than 45 because now we're dealing with 45, not with 1 through 20. And so we only get 40 options here. And so we have 40 to pick from. So that's how we figured these out. We had to think each time, each event, how many options were there? How many possible outcomes were there? Well, there was 20 for the first one, but since we can't repeat that one, now there's only 19 left. Now there's 18, 17, 15. And again, this one got a little bit bigger because we're doing 1 through 45. So to figure that out, I'm going to type in my calculator and get the value. So I'm going to do 20 times 19 times 18 times 17 times 16 times 40. And that's going to give me all the options I can get for this. So I've got quite a few, right? You can see there's a lot of options for this. So I have, what was it, 7, 4, 4, 1, 9, 2, 0, 0. So if you hundreds, thousands, that's 74 million, right? So 400,000, yeah, 74,400,000 possible Powerballs. This is why it's so hard to win games like the lottery, because that's a lot of options. If you buy one ticket, your chances are 1 in 74 million. And I think this is actually accounting for a Powerball with actually less options. I think the real powerful might use actually more numbers. I can't remember for sure. It's been a while since I looked this up. But that's the thing. Like that's why I always say you just don't play the lottery. It's not worth your time. The chances of winning anything with the lottery are so slim. 1 in 74 million. I think the published results are like this. You're more likely to get struck by lightning twice than you are to be someone that wins the Powerball. And think how many people you know that actually even get struck by lightning. You know, like it's so rare, it's so unusual, and so unlikely. But this is just the count of the number of different Powerball tickets there are to buy. You know, with this Powerball I made up here. So you can see how you can make a Powerball with only 6 numbers and have lots and lots of options. And of course, 74 million. You know, the whole country still has more people than that. So if everybody buys a lottery ticket, of course, you can kind of expect one person to win. But that's because there's so many millions of top tickets being bought. You know, when you buy one specific ticket, you're just not going to win. So I would just never spend your money on a Powerball ticket. It's just a waste of your money, really. Okay, next one. Frank needs to select batting order for 10 kids on his baseball team. How many different orderings are possible? So he's looking at 10 kids because he has to do the whole batting order. This means he's actually doing all 10 kids, right? So he's going to have 10 positions to pick. He's going to have the first person, the second, the third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. Because every single spot in the order has to be filled. You know, everybody bats. This isn't the majors where you get people replacing like the pitcher or stuff. You know, this is kids games where everybody's going to bat. When we fix the first kid, well, right off the bat, he still has, 10 kids to pick from, right? Because he has all 10 kids. But after he picks one, well, he can't pick that kid to bat twice. You know, that'd be silly. So the next person is only going to have 9 people to pick from. Next one, he's going to have 8, because now he's picked 2 kids. After he's picked 3 kids, he'll have 7 left. And I think you kind of see the pattern, right? It's just going to keep going down. 6, 5, 4, 3, 2, until he gets to the last person. And he's got 1 person left at the end. You know, this would be just how many possible orders. So there's 10 different people to pick for the first one, you know, then 9, then 8, and then okay, at the end there's only 1 possible person left. And multiplying this will tell us how many different ways we can order these 10 kids for his baseball team. Of course, this is a small baseball team with only 10 kids, and real life might have more kids. I wanted to start with a small example because I want to sit here and have to type more numbers in. Times 2. 1. So yeah, if we multiply 10 times 9 times 8 times 7 all the way down to 1, we see that we get this number, 3628800. So that's 3,628,800, and that's just with 10 kids. So you imagine if he gets 15, 25, 20, 25 kids on his team, he's gonna have way more possible combinations. It's quite hard if you're a coach or something like that trying to pick what order you put people in and stuff. There's a lot of different options. There's a lot of choices. So we're doing that quite tough. Now you probably kind of noticed that we're getting this kind of countdown pattern. This is not unusual. We see this a lot in probability. In fact, we have a way to calculate this, a way to write this because it's so common. We call this a factorial. So a factorial is an important word to know for probability, especially for these counting things we're doing right now. A factorial is when you multiply and you do the product of all decreasing positive whole numbers. So like the factorial of 4 factorial, is everything 4 down until you get to 1 multiplied. 4 times 3 times 2 times 1. Just like on the last one we saw, 10 times 9 times 8 times 7 times all the way down to 1. You could have written that as 10 factorial. We do use the exclamation point for factorial. So you write number with an exclamation point. And again, that means the product of all decreasing positive numbers, whole numbers. So we don't multiply by 0 because of course that'd be silly. You'd always get 0. And we don't multiply with negatives because you can't have a negative number of options or whatever. So that's a factorial. So n factorial, factorial, that's what it is. So if you want to do a problem like if your instructor possesses 12 ties, how many different orders can you do them? Well, you can just do 12 factorial. This works anytime you want to do the ways you can arrange all the objects. That's a big important word here. So if you want to look at the number of ways you can arrange all the objects, you're using up everything and you're not repeating. Notice that there's no repetition here. So I'm not going to use the same thing more than once. I'm using stuff up as I go. In that kind of situation where you use factorials like this, and you can actually do these on your calculator. Instead of just having to sit here and multiply 12 times 11 times 9, 10 times 9 all the way down, there's a button, the math button right here. It's really nice because the math button has a probability option. So if you go to the right until you're highlighting probability, you'll see that there's some things here, including a factorial. So option number 4 is the factorial. Now when you do this, if you hit math, go over to hit the probability, hit enter on 4, if you haven't typed anything in, it's just going to take the factorial of the last number in the previous question. I don't want to do that, so I'm going to go over here and I'm going to type my 4 over top of that, so I get 4 factorial. Or you could just type the 4 first, hit the math button, go to that probability option, go to option number 4, and then you get, I don't know why I typed 4. I meant to type 12, didn't I? I think I'm stuck on 4 because that's option number 4. Let's try that again. Let's do 12, math, probability, option number 4, sorry about that. So I get 12 factorial, that's what we were trying to go for. So I can type that in. So I usually type the number first and then look for the factorial, unless I forget and then I go back and have to do it again. And then you can see, yeah, 12 factorial is a pretty big number, and that's what you'll see with factorials. Factorials get big fast. So I think there's a limit to how far your calculator could go because factorials get so big. I want to say the limit is around like 72. Like your calculator can't handle numbers bigger than 72 factorial. If you try to do 75 factorial, the calculator will give you an error. It says I have an overflow error. Overflow is your calculator way saying that it's trying to store the number in its memory, but the number got so big that it doesn't actually have enough space in its memory to store the number. That's how big the number got. So factorials get big fast. They're really big numbers. 75 factorial is too big. I think you can do like 70 factorial and you're like still okay. But once you get past that, it's your calculator's just going to give up. It's just be like, I can't do it anymore. Oh, it doesn't even do 70. I was thinking it did 70. Well, let's see, like 68. There you go. So my calculator can handle 68 factorial, though it does have to use scientific notation, where that's really a number starting with a 2 with 96 spots after the number. That's what this little E96 means, is that there's actually 96 places after the 2. So if you ever wrote out this whole number, it would be 97 characters long if you include the 2. So it's a pretty long number, and you can see why that would start to not fit in the calculator's memory. That's a factorial. So factorial, this little exclamation point in mathematics, it means take that number and multiply it times itself all the way down. So like 6 factorial is telling us to do 6 times 5 times 4 times 3 times 2 times 1. But again, I'm just going to type that in the calculator because who wants to do all that? So I'm just going to type 6 math, that probability option 4, you get 6 factorial and find out it's 720. If you multiply all this done, you get 720. Now we're going to use some formulas here in a little bit on the next pages, where we have factorials and fractions. Now you can type these in your calculator, but sometimes you'll get like a decimal number or stuff, sometimes not. So there's a couple different ways to deal with this. One is to actually do this by hand, which sounds terrible. You're like, oh, I have to multiply this all out. Well, no, there's a trick here. The trick is noting that 6 factorial is 6 times 5 times 4 factorial, because 4 factorial just means 4, 3, 2, 1. So 6 factorial means multiplying 6 through 1. So 6 factorial, you could write it as 6, 5, and then 4 factorial, because that's what this part is. Right here, this is 4 factorial. So that's what the 4 factorial is. So what you can actually do is with a fraction like this, one of the tricks is you can write it like that, noticing that the 6 factorial has the 4 factorial in it, and then just a couple more numbers. And what you can do is you can cancel. You can say, hey, there's a 4 factorial on the top, 4 factorial on the bottom. Those cancel. This is really just 6 times 5, or 30. And you can see I didn't even need a calculator for that problem. It looked really bad when we started with a fraction and all that, but because you can cancel part of it, it actually makes the problem not so bad. So I don't even need one. Now you could do this in a calculator. So if you really don't like to do it by hand, you could type 6 factorial, and you can see how this is going to actually take me long at this point, divided by 4 factorial, because of all that going to the factorial. And you can type it in that way and get an answer. And it does give you 30. So we did it right. And you can do that, and that's fine. There are cases sometimes where maybe it might be easier to type in as a whole thing in your calculator. But just be careful when you type it in. Make sure you're always doing all the implied parentheses that are there if you have like other stuff going on besides just the factorial. A lot of times on fractions, you need the parentheses on the top or the bottom. But yeah, a lot of these you can just do by your hand. Just look at that number and say, oh, 4 factorial cancels and all that stuff is 5 times 6, and a little bit easier. Some of them we'll see have subtraction in them with parentheses. But these ones I want to point out, you always do the stuff inside parentheses first before you do anything else. So this one I would simplify. So it becomes 7 factorial over, 8 minus 5 is 3 factorial. And again, if I want to simplify this, I could just note that, the 7 is going to be 7 times 6 times 5 times 4. And then it's going to have a 3 factorial. And the 3 factorial is what's going to cancel here, right? So that's what's going to cancel. Because the 3 factorial on the bottom will always cancel with what's left of the 3 factorial on the top. This one I'm probably not going to do in my head. I could just type 7 times 6 times 5 times 4. I could just type that in and see that it's 840. So you can still work it out by hand. Or if you want to, you can type this whole thing in your calculator. You can type in 7, go to that factorial button, factorial, divided by a parentheses, 8 minus 5. If you want, you could always do that in your head if it's small numbers. If it's big numbers, it might be easier just to type it in the calculator as a parentheses. The calculator do the subtraction. But it should give you the same answer. So you can use your calculator to get these answers too. I'm just kind of showing you there's options. If you're really comfortable with a calculator, you like to use it, go ahead and do that. Just type in your calculator, that's great. If you'd rather use your by hand method where you write it out and cancel and then just multiply what's left, you're probably still going to use a calculator, but here you don't have to use a fancy calculator. You can get away with a more simplistic calculator. There is one special factorial I want to point out. You probably won't see this much, but if you do, I want you to know what it is. And that's 0 factorial, which is actually 1. And that's kind of a definition thing. Mathematicians were working factorials and looked at it and said, well, what do you do with the 0 factorial? Because it popped up in a certain situation. They go, well, to make life easier, let's make it 1. There's a lot of situations where making 0 factorial 1 makes life easier, makes the problems easier, makes things work out. So that's what we typically do. So if you see 0 factorial, we do 1. If you ever see that, and I think your calculator should be able to do that too. So if you have 0, factorial, pretty sure your calculator knows that is 1. So you could get away with typing that in your calculator as well. So again, to do factorials, the factorial button, we'd hit the math button. We go to the probability option, and there's option 4. And that's how we get that factorial. Okay, so this we use anytime you're trying to order all the things. So when I was doing all 12 of my ties, and I figured out all the different ways I could order them. When we did all 10 kids on the team, all the ways we ordered them. But notice we didn't quite do that with the Powerball because we didn't use up all 20 numbers. So this one we wouldn't have been able to use a factorial. Here we had to stop because after 5 numbers, and then before we got to the last one, we stopped. So this only works if you use up everything. The factorial by itself, it's if I'm using all the things up, I'm picking an order for all of them. Now, sometimes you might work with choosing the orders for things where some of the objects are identical. So that's what this next one's done with. So permutation rule, we call an ordered arrangement of objects a permutation. So ordering things, we call it a permutation. That's a fancy name for it. Formula below is how we find the number of permutations of R objects from a collection of N objects. So in this case, we're looking for not everything. So a permutation of R objects from N objects. So here, the big difference is not using everything. Now, technically, you can actually use this formula if you're using everything, and it will still work. But we really kind of save this one for when you're using just part of the group. So instead of picking, all 12 ties and figuring out, maybe I'll pick my 5 favorite ties I tend to wear the most, and then order those ones. How many different orders can I wear those 5 ties? Instead of choosing all 12 ties, because some of the ties I don't wear very often because I don't like them as much. So this is permutations. Big thing about permutations is they are ordered arrangements. So here the order matters. And that's what we've been doing so far, right? When we picked our batters to bat, when we picked the ties, we were looking at the number of orders for the ties. When we picked your Powerball, the order matters because if you put the numbers in the wrong order, it's not the same ticket, you don't win. Um, so that's what we're always looking for. We're looking for, in this case, we're looking for something where the order matters. And this is the formula for it. So the formula to find permutations, where you're picking R things from a set of N objects. So R is how many things we're picking, actually choosing. Out of N is how many we get to choose from. So you notice that N is always going to be bigger than R. N is always greater than R, always. Because you can't pick more than you have, right? If I have 20 kids on the team, I can't pick 21 to bat, I can only pick 20 at most. So I guess they could be equal, but if they're equal, then just go use the factorial. So typically we'll kind of use this for just when they're greater than. So what we do is we take the n factorial, so that's going to be the total number, all the kids we have, n factorial on the top, and we divide it by n minus r on the bottom. So we subtract by the difference between the two numbers, and that goes on the bottom, and that gets factorial. And that's why we'll see a lot of fractions, because of this formula, and we'll have one more formula that has a fraction as well. So this is the formula. So if I want to find this, so this is going to say we have 6p2, that means we have a collection of 6 objects, but we're only choosing 2 objects. So we're not picking everything. We're not going to pick all 6. We're just picking the first 2. So maybe I've got 6 shirts that I love, and I'm picking 2 of them to take with me on a short overnight stay or something like that. So I'm just picking my 2 favorite, and I decide which order I'm going to wear them in. That would be a have 6, choose 2 situation. That's what this is doing. So 6. I say 6, choose 2 is kind of the way we say this in mathematics a lot. And we're doing permutations, so it's a permutation. We do the n, which is the 6, so this is our n, and we do that on top first. And we do 6 factorial on top. And that's actually figuring out all the different ways you can order 6 things. But that's too many, right? Because we said we're not going to use everything, we're only going to use 2. So on the bottom, we do the subtraction, do 6 minus 2, and we subtract that. What this will do is when we divide this out, it's going to get rid of all the extra things we didn't need, because we're not using all 6 things. We're using just 2 of them for whatever reason. And there's still a factorial on the bottom. So again, you can do this by hand. You can start simplifying. You do 6 minus 2, you get 4 factorial on the bottom, 6 factorial on the top. And you can see, of course, this is similar to that one we saw before. You end up canceling the 4 factorial, and you're just left with the 6 times 5. We saw that before, where we cancel the 4 factorial. Or 30. So that would just give us 30. And that works fine. Again, if you don't like a calculator that much, if you want to do it by hand, you can usually do these by hand. You just end up with a little bit of multiplication. Sometimes you have to do a couple more numbers, but that's the idea. Really, the number on the end here will tell you how many numbers you have to multiply. So 2, you could say I multiplied 2 numbers. You only picked 2. Started off, I had 6 things to choose from. And then after I chose one, I had 5 to choose from. Notice that this is a lot like the multiplication principle. If I use that and say, okay, well, I'm picking 2 things out of a set of 6, start with 6 choices, use one up, you're left with 5 choices. And that's how we can figure out there's 30 different options. Okay, but if you like calculators, let's talk about what you do with this one. If you like calculators, you can actually do this problem with a calculator. You don't even need the formula. If you're comfortable with a calculator, this formula, you don't even need it. You go to that same math button. So that same math button we did for the other probability, because under that probability, it has the permutation formula right there, number 2. So we go to option number 2. Now again, it wants the first number beforehand. Now my calculator is kind of fancy. I got the color edition mostly because I like how it shows up on my camera. So that's why I use it. But if you have one that's not the color edition, it might already put like an A and S at the beginning. Again, that's just using the previous answer. So like I might be using like 1 on mine. So if you have a calculator that puts A and S, again, it's just trying to put a number in there automatically. You can always just go over to it, highlight it, and then type in what you want there. So I want a 6, I'm going to type a 6. And then I'm going to go over to the other box and type in my 2. And so I use my arrow keys to get to the box I want. So if I had been better and typed it ahead of time, I could have typed 6 to start with, then hit the math button, go to probability, NPR. You can see how it just puts that 6 there already. So some of you might want to do that when you're using a calculator. You might want to type the 6 first, then put the combination, the permutation, NP2, the 6p2, but type the 6 first so it just goes in the right spot to start with. Okay, once you got 6 and 2 where they're supposed to go, always the big number first, small number second. Then you should type it in and hit enter, and there you go. So it did all this calculation stuff for me. I didn't have to do that part. because the calculator will just do it. So on the calculator again, note calculator, it's going to be the math button, and then it's probability, and it's option 2, NPR. That's your permutation. That's how you do it with the calculator. Let's do one more. School has a club with 9 members. So they have 9 members on their club. You need to choose 3 members for positions of president, vice president, treasurer. Here you notice again the order matters. That's something that's important to notice when you're trying to decide whether or not you're using permutations. We don't have other calculations if the order doesn't matter. Of course, when you're trying to pick president, vice president, and treasurer, I think the order matters, right? Because one kind of person might be good for president, but might not be good for treasurer, or vice versa. So it kind of matters what order you pick them in. And we're looking for how many different ways can you fill those 3 positions. So note here that our n, number we're choosing out of, is going to be 9, right? We have 9 different members, so we have 9 people that we could choose. And we're choosing, how many are we choosing? Well, we're choosing 3 of them, right? Because we're choosing president, vice president, treasurer, we're choosing 3 members. So that's our R, that's our N. And of course, it's pretty easy to know which one's which, because always the N is the bigger number. So we do N is 9, R is 3. So when we want to use our NPR permutation formula, we just make that 9 for the N and 3 for the R. And that's how we figure that out. So 9P3. And again, I'm just going to do it with the calculator. So I'm going to do it by hand. So let's go ahead and type in my 9, hit math, go to probability, probability, hit enter, type 3, and there we go. 504. So just out of 9 people, if you're choosing 3 of them, there are 504 different ways you could pick. Again, if you want to use the multiplication rule, so this is a little side note, you don't have to do it this way, but if you really like the multiplication rule like I do, the multiplication rule, you could just think about the fact that the first person you pick, you have 9 people to pick from. The second person to pick, you have 8 people to pick from because you already picked the first person. Third person, you have 7 people to pick from. So you picked 1, there's 8 left, pick 1, there's 7 left. And you're only picking 3 people. If you multiply that out, 9 times 8 times 7, just to make you trust me, I'll show you. 9 times 8 times 7 is still 504, right? You get the same answer. So you can do this with the multiplication rule. Permutations are usually pretty easy to just turn into a multiplication rule question. So I really don't care which way you do it. If you use the permutation or you use the multiplication rule. Just when you're doing the multiplication rule, think about how many things you're picking from and how many you're actually choosing. When picking out of 9 things, only picking 3 of them. And so the multiplication rule actually works pretty good. But if you want to just use NPR, because you know how many you're picking out of and how many you're choosing, and you want to just throw it in the calculator, works just as well. So I really don't care which way you do it, because both of them give you an answer. And this one can give you kind of a pain if you're picking 15 people or whatever. You might have to type a lot of numbers in your calculator, whereas this one you only have to put the 15 down here out of how many you're picking out of. So some might be easier in that sense when you have bigger numbers to use the formula. Okay, that was permutations. Everything's different. We're picking everything just once, so there's no repetition. Order members, and that's one thing we're doing. There's no repetition. If you get to probability where they're like picking the same thing over and over again, that gets to be a different formula. But I don't think we're actually seeing any of that in our homework or anything. So every time we're going to kind of use up stuff as we go, and there's not going to be another one to use later. So that's why we're going to deal with a lot with no repetition type questions. Order matters. That's when you use permutations, because it's the way you can order things. Okay, now there is some situations where you might use a permutation, but some of the items might match, might be identical. So maybe you're trying to arrange, I think the example I have here is like colored chairs. So some of the chairs are red, some are blue, some are green. Well, you can't really tell the red chairs apart that much. So you're going to kind of treat all the red chairs as kind of being the same, but they are different than the blue chairs. In this case, we'll use a slightly different formula. So this is the formula if some of the items match, some of the items are identical. So we're doing permutation. Again, the order matters. We have a set of n items, so n is the number of total items, but some of the items are identical, so each n sub I, so that's just a way to label the different number of items that are identical, is going to be a number of identical sets. Then we'll use this formula. So this formula, I don't think your calculator really does, so you're going to have a formula on your note card to remember. This is going to be one, and again, this is for some items are identical, and it's still permutations, So we're still worried about, the order matters. And, of course, no repetition. Like I said, we're going to do mostly no repetition. Can't use the exact same chair twice. We can use two red chairs, but they'll be two different red chairs. Okay, so example. You're curious how many ways you could arrange a set of chairs for a game of musical chairs. Chairs are identical except for the color. So the only thing you can do to tell them apart is the color. And you notice that there are 4 red chairs, 3 blue chairs, and 6 green chairs. How many ways could you arrange the chairs? So how many ways could you arrange? We're looking at the number of possible arrangements. Well, first off, the n factorial is going to be the total counts. How many chairs are there? Well, if there's 4 plus 3 plus 6, that's 13 chairs total. So n is going to be 13. And then I'm going to have my n's on the bottom. I'm going to have n sub 1. Well, the first one I have 4 red chairs. N sub 2, the second one I have 3 blue chairs. And n sub 3, well, I have 6 green chairs. Those are going to be my repeats, where I have 4 identical chairs, 3 identical chairs, 6 identical chairs. So I do 13 factorial on the top. On the bottom, I'd have 4 factorial, 3 factorial, 6 factorial. So again, each one of these represents a group of things that are basically identical. Like it's hard to tell them apart, That's what those would be. This one, I'd probably just use my calculator because this is kind of a pain to simplify by hand. So I'm going to go ahead and type this in. I'm going to do my 13 factorial, so I'm going to use this math probability factorial button a lot. I'm going to do that. When I divide here, I do want to make sure all these are on the bottom. So when you're doing calculators and you're doing division and fractions like this, there's an implied parentheses around anything like this where there's multiple things on the bottom. I'm always going to type that in, because if you don't type in your calculator, just do 13 divided by 4 factorial, you don't put parentheses around here, it's going to do the division and then multiply. And we want to do the multiplication first before we divide. So we do 4 factorial. I could do that factorial bunch, like I said. 3 factorial. And if you just put them next to each other like this, I'm pretty sure, if I remember correctly, it will multiply them. So I don't need to put the times in there, because your calculator usually assumes times if you put things next to each other. Close that off, so now it should do the multiplication and then do the division. And you should get 60,060. So that makes sense. 60,060 is our answer. So this equals 60060. So 60,060. Quite a few options, right? It's less than if I just did a 13 factorial. So if I just did a 13 factorial where I use all 13 chairs and arrange them all, that one's got tons of options, right? So what is that? 6 billion options. So there's 6 billion options if all the chairs are different. If you had 13 different colored chairs or unique chairs, you'd have 6 billion ways to arrange them. But since we had some repeats, we had some chairs that matched, there's really only 60,000 ways to arrange them. So that's the difference there. Okay, so that's permutations where some of the objects, not everything, but some of them are identical. And so we have to kind of divide out those ones because it doesn't really make sense to swap. If I swap 2 red chairs, the pattern doesn't look any different. Okay, so everything we've been doing so far, we've been doing order matters. The order you put things down changes things. The last section to do on this one is when we have combinations. And a combination, what makes it different, what makes it special, is it's unordered. The order in this case does not matter. I'm just combining a bunch of things together. I don't care about the order of the things. This is like if I throw 5 shirts in my suitcase and I figure I'll just figure out what order to wear them when I get there. I'm not really putting them in there in order now. I'm just saying I'm going to pick 5 shirts. When I get there, I only have those 5 shirts, and then I can wear them whatever I want because it doesn't really matter to me. I just have 5 shirts in my suitcase. So that's something where order wouldn't matter. If I go to the drive-thru and I order a meal for my family, it doesn't really matter if I pick the kids for my meal for my son first or whatever my wife's getting first. It doesn't matter the order. I just have to pick the right set of things. Well, that's going to be a combination. The order doesn't matter. Okay, so we have a similar formula where we're looking at the number of objects we're choosing from a collection of a larger number of objects. So again, we'll still see that the n is going to be bigger than r. It could be equal. That's definitely a possibility. But in that case, you're just choosing everything. And so that's going to make it really big. So this case, you'll see we have a very similar formula. It still has the n factorial on the top. It still has the n minus r factorial on the bottom. The only difference is that it has this extra r factorial on the bottom. What that does is by putting an extra number on the bottom, you're dividing by more. and you're making the value smaller, what you're dividing it by is you're actually dividing by the number of ways you can arrange the objects you pick. So if you're picking like 5 objects, if R is 5, dividing by 5 factorial gets rid of all the different ways you could rearrange 5 objects, because order doesn't matter. So we don't care about the fact that, you know, ABC is different than CBA, because then whatever we're doing, it doesn't matter what order you pick the letters, you know, and what we're doing. So that's what this little R factorial does. It just divides out the orders. So this divides out the orders. And that's why combination has a little bit more to it, because we have to get rid of the orders. Once you get rid of the orders, all you're left with is all the distinct groups, the groups that are different. So the group of letters that would all be different. That's what I would be getting. So this one is still no repetition, but the big difference here is that order doesn't matter. So when you're doing homework and you're doing quizzes and the test, you always want to look at these questions and think, okay, does the order I'm doing them in, does it matter? Does it matter what order I'm choosing these things? If the order doesn't matter, then I'm fine. I don't have to worry about it. I use the combination rule. So here they have a question, 6 choose 2, so 6C2. Again, this is the same. We're choosing 2 objects from 6 options, choices. But here we're saying order not important. The order does not matter. I don't care what order I choose them in. I just care which 2 get chosen. So 6C2, so we can do this as we can do 6C2. If I want to do this by hand, I would put the 6 factorial on the top, just like before. I have the 6 minus 2 factorial on the bottom, just like before, but the only difference is I'd have an extra 2 factorial on the bottom. So like before, I could simplify this by hand. I can do the 6 factorial on top. I can do 6 minus 2 is 4 factorial on the bottom. And put 2 factorial. I can cancel just like before. We saw that the 6 became that 6, 5, 4 factorial, and you cancel everything but the 6 and the 5. So you have the 6 and the 5 on the top. But the difference here is after you cancel the 4 factorial, you still have a 2 factorial at the bottom. So I'd still have to take this number, multiply it, and divide it by 2 factorial. Well, 2 factorial is just 2 times 1. So that just becomes 2. This would become 6 times 5, which is 30, over 2 times 1, which is 2. And the answer is 15. You can see we actually got a smaller answer because before when we did the permutations actually gave us, here is the page. The permutations, when we did permutation 6P2, we got 30 options. When we do combinations, we only get 15 because when you have 2 objects, there's 2 ways you can arrange them, right? You can switch A, B, and B, A, and that's it. So we divided out the 2 different ways you can rearrange everything, and we got 15 distinct groups. If you don't worry about order, there's only 15 options. You could have 15 options with different things. But just like before, you can do this by hand like this. If you like to do things by hand, you don't like the calculator, there it is. If you want to use a calculator, make your life a little bit easier. This one definitely, I like using the calculator. There's some problems where doing this by hand is a real pain because you always end up with numbers on the bottom you have to divide by. I tend to just use the combination option. So I go to that math button one more time. I told you this math button, if I haven't said it, but hopefully I'm saying it right now. This math button, we use it a lot in this class for these probabilities because that's the option number 4 over here, probabilities. And you can see the third option down is your combinations. So there you go, you can do NCR. Again, mine's letting me type in the 6 first, afterwards. Yours, you might have to go back and type the 6 first before you hit the combination, just to put in the calculator a little bit. Even between the two from T84s, some of them are a little different. But yeah, once you get 6C2 like that, then you hit enter, you can see, yep, there's the 15. Just like we thought, there are 15 possible options. So again, on the calculator, we have the math, prob for probability, and the probability is the third option, so option 3. Okay, let's do a couple more combinations, and then we're done. That's what this section's all about. It's all about these factorials, the combinations, permutations, and of course that multiplication method that we talked about at the beginning, which is still powerful. You'll notice that with these guys, the combinations, that multiplication rule is not quite as easy to use. It gets a little harder to work with. So these ones I definitely use the calculator instead of trying to figure out the multiplication principle. Okay. So your professor, me, wants to put some albums onto my new smartphone. It's funny because when I wrote this, I got a new smartphone, but as the years pass, I think I got one just last month too. So So that's funny that this is, I do have another new smartphone. Actually, I already have some music on there, but anyways, I don't want to use up all my memory. Back then, my smartphone didn't have as much space, not that a bit more. So I'm going to put 5 albums, CDs is what I got them as, but albums. I'm going to put 5 on my smartphone. If I have 60 albums in my collection to choose from, how many do I have? How much different options do I have? I'm choosing 5 albums. I have 60 albums in my collection to choose from. How many different options do I have? Notice here, the order doesn't matter, right? Because I'm just putting them on the phone to use later. So I don't care which album I put on first, because when I'm done, they'll all be on the smartphone. They'll be there ready for me when I need to go listen to them or want to go listen to them. So in this case, this is definitely order doesn't matter, because I'm not picking a playlist order or something. I'm just saying I'm going to put some CDs on my phone. And you guys are like, that's a pretty old school thing to do, Mr. Autobahn. Why don't you just listen to Spotify? Well, I do, but sometimes I'm driving up through Hill City and there's no cell service. And so it's nice to have the backup music on your phone in those kind of situations. So order doesn't matter. And I'm choosing out of 60 albums. I have 60 CDs I can pick from, but I'm only choosing 5 of them. That's the difference. So that's how many I can choose out of. That's how many can I actually choose. Remember, N should always be bigger than R. So when you're using NCR or NPR, N should always be bigger than R. The first number is always the bigger number. So I'm going to do 60, C, 5, because I'm having 60, I'm going to pick 5, and that'll give me the answer. Now again, I'm not going to do this by hand because it just gets to be a pain. So instead, I'm going to type in my 60, hit that math button, go to the probability option, hit NCR, type in that 5. There we go. We have lots of options, right? This is pretty big because I have 60 CDs to pick out of. It's probably bigger now. I probably have a lot more CDs. You're like, buy CDs? Who does that anymore? I buy them at thrift stores. They're cheap. So there we go. I got 5 million options. And this is distinct options, right? So this isn't counting order. So I have 5 million different choices on which 5 CDs I could put on there. If I don't worry about order. If I'd done it with an NPR, so I've done the same thing where I chose 60 and I did NPR where I worried about order. You notice there's way more options now, right? That's 655 million, but that's worried about order, which is silly in this case. It doesn't make sense to stop and think, okay, well, if I pick CD A, B, C, D, and then pick CD, D, C, D, A, that's not different because they're the same 4 CDs. I want to put, I want to put a different set of CDs on each time. So again, order doesn't matter, so we used combination. So then there was 5 million. So you'll see the combination gives you a smaller answer. When you stop worrying about the order, you're going to have smaller results, and that's because of that extra R factorial, that extra division we did. Okay, one more example. How many different samples of size 6 can be obtained from a population of 40? And now you can hopefully see where this is kind of getting back into statistics. Like I said, next week or next section, we're going to get into taking this probability back into statistics. And one of the ways is when you're trying to pick your samples and figure out how many different options you can have. So if I'm going and I'm picking a sample group, randomly choosing a sample group, and I'm looking for a sample of size 6, and I've got a population of 40 people, it's good to know how many different samples can I pick. That way, when I need to figure out probabilities, like what's the likelihood of me getting this specific sample group, I can find those probabilities. So here, my population is going to be my n, because n is always how many you're choosing out of, so 40 is going to be the n. 6 is going to be my sample size, so R is going to be 6. And notice here that the order doesn't really matter in this case, because I don't care what order I pick these people to give them a survey or ask them questions. I'm going to collect all the data anyways and process it together anyway, so I really don't care about the order. So in this case, order is not going to matter. So that's why this is definitely going to be an NCR, a combination, where the order doesn't matter. I'm going to do 40, C, 6. We're going to find out how many different groups of 6 people or objects or whatever can be sampled from a group of 40 populations. I'm going to do 40, do that probability, NCR, 6, 40C6, and I get quite a few, right? There's 38, 38, 38. It's an interesting number. So 380, 838. So 3,838,000 different ways you could pick 6 people out of a group of 40 people. That's only 40 people. If you think of a population of like thousands or millions, you can see how the math gets kind of tough and why it's nice to have a calculator to be able to do things like figure out the number of options for you. So that's it for this section. It's all about counting. Again, you need to know that multiplication rule, how if you know the number of options for each part, you can multiply those together to get the total number of options. You know that factorial, when you're picking all the objects, using them all up, then you just do the factorial, and that finds the count for everything. Permutations, the order matters, and we're not choosing everything, so we do that one. And then the combinations, where order doesn't matter, and we're not choosing everything, so we use that formula. So that's what you need to know for this last section of probability. So that's it for this section. We're moving on to chapter 5 after this. I'll see you on the next set.